macro world. M-A-C-R-O. Macro means bigger and bigger and bigger. But you can ask, should we begin only with centimeter scale? Suppose we contract the scales? Yes, we can. And when we contract the scale, we find that there are not too many objects as such, on their own, which are much, yes, you may come to the, like microns. So we go to a scale which is called micron. Micron is 10 to the power minus 6 meters. Micro means 1/1,000,000th of the size of a meter. We are now not going to the expanding scale, but we are now going to what you call contracting scales. Now, many of the devices that you have in this mobile phone, they are of the sizes of that order. Many of them. There are, and that is what at one time we used to call them microelectronics. That is, we have here devices whose operations are determined by small components, which may be of the order of 10 to the power minus 6 meters, or 10 to the power minus 4 centimeters. And that is a contracting scale that we are going towards. Now, micro world also has not these components alone, but there are many other objects which are small. And these objects are things like dust particles. These are very small. Today, the viruses about which people are talking more about, of course, viruses have been there. Viruses have been there. There are many viruses without, perhaps without the existence of certain viruses, life may not have evolved, life may not exist also. So there are viruses whose sizes may be of the order of microns. Then there are droplets. Droplets are of this order of microns. Dust particles are of the order of microns. And then you can contract further and further and further. Now, this is something we know for sure, that yes, this is possible, that matter can be divided into smaller and smaller and smaller sizes. But the fact that once you divide into smaller and smaller particles, the nature of the physics and the nature of the dynamics would radically change. It was not known until about the turn of the last century. It is not only known, they were very surprised that all the mechanics that we knew, mechanics based on of the macro world, and macro world's mechanics is more or less given by Newton's 3 laws of motion. It is very interesting for all of you to understand that how Newton discovered, or not Newton, how we discovered these laws, etc. That is a different kind of story. But it was around the turn of 1890s, late 1890s, you can say, more so from 1897, that people understood that yes, the laws that we know of Newton are not going to apply when we come to objects which are smaller and smaller and smaller size. But how small, that was still not. How small an object should be in order that you can say, you have said that I have entered the quantum world. That, of course, people still did not know in around year 1900 or so. And so. Now, idea is, how did we suddenly stumble? The way we stumbled has also a certain path. It is not that one day suddenly things fall, like Newton's apple, as I said, which is a myth that Newton learned it from the apple. It's a myth. It is a story that people have, very interesting story people have made. Just as all our lives, we hear stories. And some of the very interesting stories can be found in, in India. For example, stories from the Ramayana, Mahabharata. Ramayana, Mahabharata have different kinds of stories. Not that I believe in these stories. That is not my point. The issue is this, that one story leads to another, another story leads to another, and they branch off in many directions, and they again join, then again branch off. Now, when you have to enter the quantum world, how we came to know about this quantum world, it is something of that kind. You will sometimes find a problem that where to begin, and perhaps where to begin is easier, but then to say in which direction to go to complete the story, or to, and having completed the story, having gone a certain far, then you might find that yes, we have to come back to them, to somewhere else, and from there again begin a story, and where to join them together. So all this we have to see if we have to have a, even reach the quantum world. Even to reach the quantum world, we have to do that. Now, the first thing that took place was around the year 1800. There was a very well-known British scientist. His name was John Dalton. And he said that once you keep on cutting any object into smaller and smaller and smaller parts, then you will reach a point where you cannot cut it further. You cannot cut it further. And once that happens, you have reached that, then all the characteristics of the material will be decided by the smallest unit to which you have been able to cut. And that is how came two very important ideas. One idea was the idea of the molecule, and another idea was of the idea, it was not a discovery of the atom. He suggested, people had to wait a long time. Still we cannot see atoms. Okay, discovery have to be found very indirectly. They're not a directly. He first said that there's something in atom, and this is very different from whether people earlier had said. Centuries ago, the Greeks had said, and it is said that Indian philosophers had also said that matter, when once you keep cutting, you will end at a certain point beyond which you cannot cut. Now, you know, there is a difference between a thought and between what is science. Once you go to your higher level in school, your teacher would do, maybe, I don't know whether teachers still do it, but at least my teacher used to tell in chemistry classes that divide your notebook into 3 vertical lines. And the one on the left side, you put experiment, middle one is observation, and extreme right one is called inference. That is, since the time of Galileo and Newton, we advance science not purely by thought processes, but from the point of view of experiments, observations, inference. Now, ancient Greek philosophers had no experiments to perform. They gave it as a thought. But when you come to the case of Dalton, as somebody has said, he did not know how to perform experiments. But there was a certain thing that is known, that different objects have different properties. And where does these properties lie? If the properties have to lie somewhere, the Dalton's idea was that they should lie fundamentally in the basic unit by which matter is composed. And therefore, people came to understand there is something called a molecule and there are something called an element. A molecule is composed of several elements. For example, I have told you about hydrogen. Hydro means water. Gen means something which generates. And it was known that hydrogen and oxygen, that they combine. But they understood that hydrogen is a fundamental unit for forming water, and oxygen is another fundamental unit for forming water. So therefore, these are the two fundamental units which combine together and they form another unit. I won't say it is fundamental, another unit, and that unit's name is the molecule. The molecule, the water molecule. And this water molecule begins to behave as another unit, and its properties are completely different from the properties of hydrogen and oxygen, by whose combinations we had made water. So therefore, we came into what are called units. When we talk of the solar system, we need not bother about what happens on the surface of the earth. We can take our entire earth as one unit. We need not bother what is happening inside the earth. So earth becomes one unit. And earth as one full unit goes around the sun. Similarly here, when we talk of water, water begins a unit and water has its own behavior, and that behaviors are completely characteristic of water. And water is water because it has got hydrogen and oxygen, but all its properties are completely different from the properties of hydrogen and oxygen. Similarly, if you talk of hydrochloric acid, it behaves as a as a unit, and that unit is a molecule of hydrochloric acid, and its properties are completely different, not only of that of water, but also of hydrogen and chlorine with which they are formed. And not only do they combine, the atoms can combine to form another unit, but also with heat, they can be dissociated to separate them into units. So that is why hydrochloric acid, if you heat very strongly to about 1,000 degrees centigrade, it will disintegrate, giving back hydrogen and chlorine. And similarly with water. Water, if it be heated to very high temperatures, it will dissociate and give us once again. So therefore, we are talking of units. Question was, how big are these units? It was not known. It was known only Dalton had given the idea, but Dalton had no idea that how big these units are. And for that, how big these units are, we had to wait for indirect evidence. And this indirect evidence came much later. And that was it had to wait about very close to 100 years. Because there were some people in 1880s, 1890s, they were even questioning that, no, there's nothing called an atom. They were questioning about that there's nothing called an atom, though Dalton had said 1800, because you had to prove an evidence. I will not go into the evidence part, but the evidence came in a different form, and this had very little to do with the composition of atoms or molecules. They came from the ideas from a completely different area, and that is the area of properties of gases and liquids. It was, why is a gas a gas? What happens in a gas? What creates a temperature of a gas? What creates the pressure in a gas? These were the questions that in the 18th century people were asking, and we came to know that all these properties of the gases are because that a gas has to be, because molecules in the gas keep moving about. How fast they are moving about, etc., or what is the kinetic energy, or how much momentum they transfer on the wall of a container. All these are the ones that explain that their atoms are there, but nobody had till that time seen an atom. So the micro scale that we were entering was the scale of atoms and molecules. They are not seen, but we understood that they're there. And there is the question that the thought is also a very important part in the advance of science. But thought alone cannot advance. So there were, by that time, many of you would have come to know about it in your school, that we knew that there is something called Boyle's law and Charles' law. These laws are there. These connect pressure, volume, and temperature, pressure, density, and temperature of a gas. And these properties of gases, called the Boyle's law and the Charles' law, could be explained in terms of the ideas that a gas is composed of molecules which move around and they hit the wall of a container, and that is how pressure is created, and how and faster they move, the temperature is higher. These were the very fundamental ideas which told us, yes, there are atoms, but we did not still know of atom. We have not still seen atom nor a molecule. Why couldn't we see? Because again, it comes to the scale. Because scales are so small. And scales are so small, not merely in terms of how big or small they are, but also how heavy they are. They are also very light objects. So these are, again, the ideas that we require to keep in mind as we come towards deeper and deeper into the quantum world. Now, how did we know finally that there are atoms and molecules? Boyle's law, Charles' law of gases, yes, they told us, but there came the other questions, and this is about the properties of gases and liquids. How does a liquid finally unheated become a vapor, or a vapor? How on being cooled, does it become? How does it become a liquid? These were the questions that were there, and there was a very strange thing that people saw. Earlier, people thought that if you apply more pressure, any gas could be made into a liquid. But later it was found that, especially with carbon dioxide, there were some classic experiments done by a person called Andrew, and he found that even if you compress carbon dioxide more and more, it refuses to become a liquid unless it is cooled sufficiently. And this question of a critical, we know of all pressure, boiling temperature, and condensation temperatures, etc. But nothing can change from a vapor to liquid or a liquid to vapor unless pressure and temperature, both, very important, both have what is a critical point. How to understand that? People could not, until there came a very well-known great scientist. His name was van der Waals. And it was van der Waals who first said that we have considered till now that atoms and molecules are very small. They're small. But till now, we have considered that they have no size and no size at all. But that is not true. Atoms and molecules have a definite no matter how small, but they have a definite size. And when he used this concept, he could immediately explain the vaporization of gas and condensation of liquids. He could explain the idea of a critical point, and everything fell in place. So that is what it showed to us, is that though we could not still see an atom, but the idea of an atom and its given size, and this size is non-zero, was very atom or molecule, that its size is non-zero, was important or essential to explain a macroscopic phenomenon, that is boiling and vaporization and condensation of liquids. So therefore, even though we could not see an atom, we understood that the atoms must be there, or molecules must be there, they must be having a given size, and without that size, without that, we cannot have vaporization and condensation of fluids. So gases and liquids, we call them fluids. A gas is a fluid, a liquid also is a fluid. So therefore, even though we have not seen an atom, we have now as at least an evidence that an atom exists. Dalton had said an atoms exist. We found an indirect evidence from the gas laws, and now we have got another indirect evidence from the point of view of or idea of vaporization and condensation processes in fluids. But then there are ideas that a fluid not only vaporizes and condenses, but it has got other properties. And this one of the properties is that of diffusion. Another property is that of thermal conductivity, that it conducts heat, then viscosity, etc. The thermal conductivity, it was understood, and all these properties, it was understood, take place because of collisions between the particles in a gas. That atoms and molecules collide against each other, and that is how the ideas of diffusion, viscosity, etc. come. I would not talk of viscosity and thermal conductivity, but diffusion is a process that many of us can see. And you can try it as a very small experiment. And it is this: take a very tiny piece of a sugar crystal, take a very tiny piece of a sugar crystal or a candy, and so on, put it in a glass, and fill the glass with water. What you would see, that now if you take a spoon and taste the water from the top, you may not have the sweetest taste. But and please again, don't stir the liquid. What I'm talking, not stirring, just keeping it as it is. And very gently you put the spoon inside, and deeper you go and extract, if you are able to extract very, very quickly, or dip your finger inside, and you find the top part is still not sweet, but the lower part is sweet. And how does it happen? This is happening by a process which is called diffusion. That is, when there is water and there is sugar below, so it dissolves. And this dissolves, since I have not stirred, is by diffusion. That it detaches, sugar detaches out from the solid sugar from its surface and gradually moves inside the liquid. But how do they move? Only way it is possible is the molecules in the liquid, they come and hit the molecules of sugar and then knock them about. And that is how the one which has just got detached and which is at the bottom, which is just at the bottom of the glass, it has been knocked up, and brought up. The other way you can see, of course, is that when you light a matchstick, some smoke might come. Or what in India we often do very often, it is called agarbatti. Agarbatti, I think in Tamil you may call things like samrani and all that. So if you just light it, you find that a smoke comes out, but the smoke gradually spreads. Now this is a process, yes, incense stick. So this smoke uh, actually spreads. How does it spread? What makes it spread? It is all because as you have created the smoke, which is in a vapor form, it is dark because they may have some particles also in it. Those particles are being hit by other gas molecules and they are kicked in all directions, and this process is called diffusion. Einstein's first great work was on this, and this motion is called Brownian motion. And Einstein explained the principle of diffusion by this Brownian motion. That is, here are molecules, and molecules are being kicked around by other molecules, and that is how the process of mixing takes place. That is how fluids get viscosity, and that is how fluids also get their thermal conductivity. And how big they have, how to calculate them, that was given by Einstein's theory of Brownian motion. It is one of the fundamental works. And not only that, Einstein's theory of Brownian motion gave us a way to calculate the diameters of molecules. Till that time, we did not have a method to calculate. Of course, indirectly, we could say that yes, it can be so much from vaporization properties, etc. But it was a very direct way that Einstein gave, that how to calculate the diameters of atoms, molecules, by experimentally studying their diffusion constants, viscosities, and thermal conductivities. This is a fundamental work that was done. So with that work, what we came to know, that yes, there is no question of denying that an atom exists. So it was an experiment which finally could lead to an inference. And you can see that from the time of Dalton, who gave it in the year 1800, to arrive at a complete inference about the existence of atoms and molecules, it took 1905, it came with Einstein's famous work. And so therefore, it is a journey of 105 years by the time we arrived with the most elementary microscopic object, and that is a molecule. And then comes a question from the molecule, how to get into the water. Really, the molecule and water makes the units from which our understanding of the quantum world actually begins. It actually begins from there. But this history is important because people still they knew that there can be an atom, or there can be a molecule, Still people were not very sure that yes, it can be a thought, but do they really exist? Well, fine. So this is one route of the story that I said. But this route just gives a certain background of the quantum world, but it still has not opened the windows to the quantum. So till now, people had thought that, okay, atom is there and the molecule is there, but atom and the molecule both are indestructible. That an atom will exist like this, it cannot be subdivided. Molecule is there, and molecule can be split only into atoms. And once they're split into atoms, They cannot be subdivided anymore. But then, really as a shock, it was really a shock that came in the year 1897, when Sir J.J. Thomson could show that no, atoms have inside them a charged particle, and that is the electron. He discovered in the year 1897, and once you understood, once you got the complete evidence that an atom has an electron, it was a complete shock. Because nobody till that time had believed that atom could be split. And now it is split. It is something inside it. So what is happening? And that is where the entry into real quantum world comes in. Because the electron that was found, there are no other charge, no other particle has been found which is smaller than the electron and which has a charge lower than the charge of the electron. That is why we call an electron as a fundamental charge. There has been no charge discovered which is smaller than the electron, and there is no mass considered found which is lighter than the electron. And the ratio of this quantity, this is a very important quantity. You may just note it, you'll understand maybe as you progress through higher classes, that is we call something called charge by mass ratio. That is E by M. E is electron, M, the electron charge, and M is the electron mass. This E by M ratio is the same for any charged particle that you get from any atom. This is important, that E by M of the charged particle, of the fundamental charged particle that you get from any atomic system, that is whether you get from hydrogen gas, whether you get from oxygen by ionizing oxygen, whether you get by ionizing chlorine, the fundamental charge E by M that you get is found to be the same irrespective of which substance you get it from. And that is another landmark, that it is not only is an atom split or atom can have, we have found that atom also has a particle. But this particle called the electron is present in every atom. In every atom, this small particle and its mass is something of the order of 9 multiplied by 10 to the power minus 28 grams. This small particle, this tiny particle, which is a fundamental of charge, is present there in every atom, and therefore it is a universal charge. So universality is something very important in science. And with this idea of universality, we are actually entering into the quantum world. Because if an atom is neutral, which it is, but if inside the atom, if there is an electron, which is the negatively charged particle, then the atom must have a positive charge also. And therefore, it was understood that there must be some positive charge inside. But how is it is like a small positive charge? Where does it reside? Is atom like a small, is the atom like, yes, ions are there. When atom is stripped of electrons, we get ions. These are called ions and electrons. So where is this? So there must be some positive charge. And this positive charge is called a proton. But how is it? Is that entire positive charge uniformly smeared inside the atom? This was a question people did not know. And this was another important question for understanding the quantum world. So many people, like J.J. Thomson, who was the discoverer of the electron, he believed that all these positive charges inside the atom are smeared out uniformly, just as we may get in clouds. Clouds have electricity, but are these? But then some. There was another great scientist. His name was Ernst Rutherford. He did an experiment. He bombarded gold foils with alpha particles. Alpha particles are some charged particles. And once he bombarded them, he had anticipated that if it was a completely smooth distribution of charges, then charges will go in, enter the atom, would be bent a little bit, then as it progresses, bent a little bit, again bent a little bit, and then finally they would bend by a very small angle. But when he did the experiment, he found that true, that most of them bend by a small angle, but there are few, one in 100,000, which bend by about more than 90 degrees or even more. That is, they turn back, they're just shot backwards. Now, this could not be understood if the charge inside, the positive charge inside the atom was smeared uniformly. So his only conclusion was that positive charge is not smeared inside, but this resides in a very small region, and that region is extremely small, and that is what we now call the nucleus. So you see, this is covered. We have just entered, and this is another very fundamental idea of the quantum world, that as you come to a smaller scale, and how small is that scale? That scale is of the order of 10 to the power minus 8 centimeters. Roughly, all our atoms are of that size. Like hydrogen atoms size is about 0.5 into 10 to the power minus 8 centimeters. And this 10 to the power minus 8 centimeters now becomes one of our length scales. And that unit, we call it as the angstrom. It is called angstrom. 10 to the power minus 8 centimeters is an angstrom. So you see, our quantum world immediately defined a new length scale. And that length scale is 10 to the power minus 8 centimeters. It defined a charge, a fundamental charge, and that is the charge of the electron. And it defined a mass, and that mass is the mass of the electron, and that is very close to 9 into 10 to the power minus 28 grams. So when you talk of the quantum world, you have to think in these length scales. And apart from that, we have talked of the mass. In Newton's time, we have talked of mass, we talked of length, we talked of time. But now we enter a world, it is not only mass, length, and time comes, but another new concept comes, new fundamental, and the charge also comes. It was not in the Newton. It was not known that how charge will enter into understanding a new world. This did not know, was not known. But we have not yet told you about one more important thing that physics or science always deals with, and that is time. I've told you our mass of the electron, I've said about the length scale, it is of the order 10 to the minus 8 centimeters. But what about the time? Time I have not yet said. And it is as we go deeper into the quantum world, what are the time scales inside the quantum world or atomic world, that will get defined. And that from there, the journey of a different kind in a different direction has to begin. And if you are interested, we can take that journey also some other time. But this is a journey where you have reached from one point to another. And from here, the road can go in different directions. What direction you will take, You have to decide which direction you take. And you have to proceed along that. But after you proceeded a certain distance, you have to come back to the same point and take another road. And again come back to this point and take another road. And unless you take all these different routes, the quantum world is not complete. So we have reached today a point from where we know that yes, we are in crossroads. And from this crossroads, we have to travel in all the directions. And only then we will get to the ideas of what I think Omkar had said, quarks and etc. Okay? Quarks are certain ideas, but do they really exist? Where is the evidence? In order to do that, we have to travel along all these crossroads. Come back. Yes, crossroads is a very familiar word. Those of you are in Bangalore, you talk only into main road and crossroads, isn't it? 13th cross, 4th main, that's my address. Correct? So I'm more familiar with those kinds of words which are perfectly Indian English vocabulary. So we are now at where? Majestic's crossroads at some point. And let us see in which direction to go. Okay, shall we stop here today?
Yes, we can stop here. And I think we, next couple of sessions, Professor, can we still do the quantum
Yeah,
I mean, like a discussion on that. Because I think this is a good stopping point. Does anybody have any questions? I saw one earlier where they were discussing this unit called Planck and how small it is.
There are two things. There's something called Planck constant.
Right.
And that journey has not yet begun. Okay. And Planck constant would be another thing which has to be defined. And it comes from a completely unexpected source. And that source has no connection with what we have said.
Okay.
So that's what I said. From crossroads, we are at crossroads. And you have to take one journey, review, come back, take another journey from the same point. Okay. It is not a one-directional path anymore. Till now, we could succeed in giving a one-dimensional path, as if we are proceeding in one direction. From now onwards, it is not possible at all. Okay?
I have a question.
Please.
What is the difference between the quantum world and quantum physics?
Physics of the quantum world is quantum physics. And that physics has to be determined by these quantities which I said: the charge of the electron, mass of the electron, and the length scales that I said is 10 to the power minus 8 centimeters. And there will be a time scale which I have not yet introduced. So within this limits of 10 to the power minus 8 centimeters, masses of the order of 9 into minus 28 grams, the physics that operate, and of course the charge of the electron comes, the nature of the physics that operates there is the physics of the quantum world. And in order to understand the quantum world, there's something is missing, as I said, and that missing point is what is the time scale. So time scale I have not yet told, and the time scale will get defined once we introduce another issue, and that is called Planck's Planck's constant, which is another fundamental constant in science, about which we never knew before before the year 1900. So all these together define what the physics of this regime, that is 10 to the power minus 8 centimeters length scale, that is then mass roughly of the order 9 into minus 10 to the power minus 27 grams, and the time scale which I will tell later. All these define the quantum world, and the physics of this particular quantum world is quantum physics. Okay, please.
Okay, thank you.
And we'll have another couple of sessions as well. We'll send out details. We can have next few sessions on this as well.
Okay, thank you very much. Thank you.
Yeah. Yeah, thank you.
Bye bye. Thanks.
Bye, everyone.